Lubricants act to reduce friction. Now, this makes it easier to keep machines running smoothly, and it cuts down on the amount of heat and wear caused by friction. A machine's moving parts generally experience three types of friction: sliding, rolling, and fluid. Now, sliding friction occurs when two surfaces in contact slide past each other. This type of friction offers the most resistance to motion, so machinery is usually built to minimize or eliminate it. One way of building a machine to minimize sliding friction is to place rolling elements between the moving surfaces. This is the principle behind rolling contact bearings. Rolling contact bearings experience rolling friction that is considerably less severe than sliding friction. Still, they must be properly lubricated to reduce heat and wear. The useful life of a rolling contact or anti-friction bearing would be drastically shortened if the bearing were operated dry. Another way to build a machine to reduce friction is to separate two sliding surfaces by a film of lubricant. As long as the surfaces do not touch, sliding friction is eliminated. There's still some fluid friction within the lubricant, but it's much less than sliding friction. Fluid friction is the resistance to motion that exists within a fluid, and it's not as obvious as other types of friction. Besides lubricants' three basic functions, reducing friction, heat, and wear, they perform other jobs. They serve as hydraulic mediums, and they prevent dirt and corrosion-causing contaminants from coming in contact with moving surfaces. A hydraulic medium is like the brake fluid in your car that transfers force from the brake pedal to the brakes on the wheels. In a hydraulic medium, the main function of the lubricant is to transfer force, not just to make things slippery. The presence of a lubricant prevents dirt and corrosion-causing contaminants from touching the moving surfaces. When fresh lubricant flows between moving surfaces, the lubricant tends to flush dirt and contaminants away. Well, now that we've discussed their functions, let's talk about the different kinds of lubricants. There are three general kinds of lubricants: liquid, semi-solid, and solid. Now, liquid lubricants are oils. There are many varieties of oils, and we'll cover them later. Semi-solid lubricants are greases, while solid lubricants include metal elements and several kinds of solid chemicals. We'll discuss these varieties later. For now, remember that lubricants can be liquid, semi-solid, or solid. Well, to wrap up, lubricate means to make smooth or slippery, or to apply a lubricant. A lubricant is a substance that reduces friction, heat, and wear. By doing so, lubricants help machine parts work properly. We'll take some time now to go over all of the material and clear up any questions or problems you might have. Lubricants are made from one of four groups of materials: animal, vegetable, mineral, and synthetic. Originally, animal and vegetable lubricants were the most widely used, but they've been almost completely replaced by mineral and synthetic types, neither of which decompose as easily. Animal lubricants include those made of fats from animals like cattle, sheep, or hogs, and lard is one example of this kind of lubricant. Animal lubricants can be labeled by the kind of animal fat used and whether it is hard or soft. Lubricants made from vegetables are vegetable oils. Processing various vegetables produces lubricants like olive oil, castor oil, linseed oil. Mineral oils are petroleum products and come from refined crude oil. Most of the lubricants you'll work with in your plant will be mineral oils. Because of their stability, mineral oils perform their lubricating functions under high temperature and pressure. Synthetics are man-made lubricants. They're manufactured from a mineral oil base or from other non-petroleum-based substances. We'll talk about some of the other substances a bit later. Right now, though, we must understand the four common properties of these lubricants: viscosity, flash point, fire point, and pour point. The viscosity is a measure of the resistance of a fluid to flow. A thick fluid, like the oil here, has a high viscosity, while a thin fluid, like this oil, has a low one. The thinner the fluid, the lower its viscosity. Choosing a lubricant with the right viscosity is important because a lubricant that is too thin will not work properly, while one that is too thick will cause too much fluid friction. Viscosity is related to fluid friction. A liquid with high viscosity will produce more fluid friction than a liquid with low viscosity. Too much fluid friction causes overheating, makes it harder to start a machine. Choosing the lubricant with the right viscosity is complicated because viscosity is affected by the fluid's temperature and pressure. Higher temperatures mean lower viscosity because lubricants will thin as the temperature increases. On the other hand, if the lubricant thickens from lower temperatures, it will not lubricate properly and a thinner one must be used. Now the oil here has been heated. Notice how easily it pours into this container. Okay. Now, this oil is cold. The lower temperature has thickened the oil, raising its viscosity, and it pours more slowly. Now, if a lubricant is used where temperatures change rapidly, the viscosity index is important. The viscosity index is a measure of how thick or thin the lubricant gets when the temperature changes. Viscosity index helps in choosing what oil should be used under certain temperature conditions. An oil whose viscosity changes a small amount when the temperature changes has a high viscosity index. If an oil's viscosity changes greatly as the temperature changes, it has a low viscosity index. Now, pressure's effect on viscosity is the opposite of temperature's effect. When pressure goes up, viscosity also goes up. This is a factor in high pressure systems where thin oils are used because they will thicken enough to work properly at operating pressures. Also, high loads can create high pressure in a lubricant. If the lubricant is too thick, the resulting increase in viscosity could prevent the lubricant from working properly. This could cause equipment failure. Viscosity is a lubricant's most critical property, but the flash point, fire point, and the pour point are also important. Flash point is the temperature at which a lubricant's vapor will ignite when exposed to flame. At this temperature, only the vapor will burn. Here we have a sample of oil that is being heated. When it reaches the flash point, the oil vapor can be ignited. Fire point is the slightly higher temperature at which the lubricant will burn steadily when exposed to a flame. This occurs because enough vapor is created to cause continued burning. Both flash point and fire point are important to know for safety reasons. If flash point and fire point are exceeded, a fire hazard exists. A pour point is the lowest temperature at which a lubricant will pour. Below the pour point, a lubricant will have thickened too much to flow by gravity. The pour point is especially important in machinery that must run in cold weather. Viscosity, flash point, fire point, and pour point are four properties of lubricants. Now it's time to discuss the factors that determine lubricant selection. Basically, four things must be considered: pressure, speed, temperature, and environment. Pressure affects the selection of a lubricant because it changes a lubricant's viscosity. The greater the pressure, the greater the viscosity. Speed is a selection factor because there is a higher rate of wear at high speeds than at slower speeds. As a result, a lubricant used in a high-speed situation must be able to handle extra punishment. Temperature, like pressure, affects a lubricant's viscosity. Both normal temperature and any possible variations must be considered when selecting a lubricant. This is where the viscosity index comes in. Flash point, fire point, and pour point help determine the temperatures at which a lubricant can be used. The lubricant's surroundings or environment is the fourth factor. Certain lubricants are better in dirtier or dustier areas, and there are other environmental considerations. These include whether the equipment is mobile and what kind of atmospheric conditions exist. You'll need this information to avoid errors and to understand why a particular lubricant is used. However, you won't normally make the final decision. Usually, a lubricant supplier will help decide what lubricants are to be used in any particular place. Most plants have surveys made by the suppliers, and the results of these surveys serve as guides for selecting lubricants. You need to understand the basic reasons why particular lubricants are chosen, because you are the ones who will be doing the lubrication. We haven't finished talking about the things that make lubricants different. One of these is lubricant additives. An additive is a material added to a lubricant to improve its properties. Additives are used to help lubricants withstand the large loads and severe operating conditions often found in modern plants. Additives can lower pour point, alter viscosity, and perform other helpful functions. Keep in mind, though, that additives in lubricants may not be compatible. When adding lubricant to a partially full system, the same type of lubricant must be used. Never mix different lubricants. Be sure that lubricant added to a system is the right one for that system, that is, compatible with the lubricant already there. Additives are explained more fully in your text. We've now covered 4 groups of lubricants materials: animal, vegetable, mineral, and synthetic, and 4 properties of lubricants: viscosity and the viscosity index, flash point, fire point, and pour point. We also went over 4 factors that affect lubricant selection: pressure, speed, temperature, and environment. So why don't you take some time now to read through all of the material we've discussed so far. So far, we've talked about lubricants in general. And now we're going to talk specifically about oils. Oils are liquid lubricants, and mineral oils, which are petroleum-based, are the ones most commonly used. Their greater stability makes them more reliable than animal or vegetable oils. And they're cheaper than synthetic oils. You can categorize oils by their use, but these categories are not clearly defined. The right oil for a particular job depends on specific design, construction, and operating factors that vary from case to case. Pressure, speed, temperature, and environment must be considered when selecting an oil. We'll separate general purpose oils into 4 categories: circulating, gear, engine, and spindle oils. Each of these are used differently and may have different properties depending on their use. Circulating oil can be divided into 2 types: circulating lube oil and hydraulic oil. Both of these are classed as circulating oils because they circulate through a piping system or move freely within a closed area. Sometimes the oil in one system is used for both lubrication and hydraulics. For instance, steam turbines are built to use the same oil for lubrication and hydraulic control. However, these oils are not always interchangeable. Gear oil is a general purpose oil because it has many uses. Often, gear oil will be high viscosity. There are many kinds of gears, and each can be used under a variety of operating conditions. Now, those operating conditions determine the characteristics of the lubricating oil used. Gear oils almost always contain extreme pressure additives, so they can operate under high pressures that occur when gear teeth mesh. Engine oil is also used in different ways in various engines and machines. An engine oil is likely to be used where the working environment subjects the oil to severe conditions. Severe operating conditions make it necessary to periodically replace the oil. Spindle oil is used to lubricate bearings on small shafts, especially when the shafts are turning at high speeds. These shafts are often called spindles. Spindle oil is highly refined mineral oil with low viscosity. It can be used for lubricating delicate instruments and other sensitive equipment. Besides the 4 general purpose oils, there are different special purpose oils. Special purpose oils have characteristics that make them suitable for specific service conditions. Some of these special purpose oils are covered in your text. Remember, though, that every oil has a special purpose because each oil's characteristics are considered before the oil is used under certain service conditions. Now that covers some of the classifications of oils. Now let's discuss the most important way that oil provides lubrication. Film lubrication. Film lubrication is the separation of moving and stationary surfaces within a bearing of an oil film. It is the preferred lubrication method in any bearing. A bearing built so that surfaces can be separated by an oil film will carry more load than a bearing whose surfaces rub against each other. Now let's take a look at how this works in a plain journal bearing. A plain journal bearing consists of a bearing sleeve which surrounds a shaft. The space between the bearing and the shaft is filled with lubricating oil. When the shaft is at rest, most of the oil is squeezed out from between the shaft and the bearing by the weight of the shaft. When this happens, the bearing and shaft are in metal-to-metal contact. When the shaft begins to roll, its motion drags oil underneath it. Oil sticks to the shaft as it turns and is carried between the two surfaces. The shaft is lifted away from the surface of the bearing by a film of oil. As the rotational speed increases, more and more oil is drawn under the shaft. It forms a wedge of oil that keeps the surfaces of the shaft and bearing apart. This wedge-shaped oil layer supports the shaft and prevents it from touching the bearing surface. Oil is also used to lubricate anti-friction or rolling contact bearings. Here, full film lubrication usually doesn't occur. Only enough oil is supplied to keep the bearing surfaces wetted. There are 2 reasons for this. The amount of friction produced in an anti-friction bearing is reduced by the rolling action of the bearing's balls or rollers. Since very little sliding takes place, not as much lubricant is needed to reduce friction. The other reason is that too much oil in an anti-friction bearing could make it overheat. If an anti-friction bearing were completely filled with oil, the balls or rollers would have to push the oil aside as they turned within the bearing, and this creates more friction than occurs when you use less oil. Well, we've covered some of the ways that oils are categorized and talked about 4 general purpose oils: circulating, gear, engine, and spindle oils. We also showed the lubrication of a plain journal bearing and an anti-friction bearing. Take some time now to go over this material in your text and to read this segment on special purpose oils. Oh, now is also a good opportunity to talk with your instructor about any problems or questions you have. Well, we've seen what oils are and how they're used, but oil is not the only lubricant found in your plant. Greases are also common, and you need to know what they are and how they're chosen and why they're used. Well, let's start with a description. Normally, grease is a semi-solid lubricant made from a liquid lubricant and a thickening agent. Under some conditions, it can be solid, but usually it's in a gel-like state. The liquid lubricant used is generally a mineral oil, and the most common thickener is a form of soap. A grease thickening soap is a combination of a fat and a chemical element. The fat is typically animal fat, but vegetable or synthetic fats can also be used. The chemical elements are usually calcium, sodium, barium, or lithium, and they significantly affect how the grease is used. The important properties of grease are its melting point and its consistency. The grease's melting point is called its drop point because of the method used to measure it. The grease is heated slowly until fluid begins to drop from it. The temperature at which the drops form is the drop point. Now, a grease's drop point is an important physical property because you don't want grease to liquefy while it's in use. If the operating temperature of an area is higher than the grease's drop point, the grease would tend to flow away from the area where it was needed for lubrication. Consistency or stiffness is an important physical property for much the same reason. If a grease is too hard, it will be difficult to apply. If it is too soft, it will be difficult to keep where it is needed. Either of these situations could result in inadequate lubrication. That could result in the failure of the lubricated parts. Well, you might be wondering why we bother to use grease at all. Well, there are 4 reasons, all of which depend on the lubricant's operating conditions. Grease may be necessary to be sure that lubricant will stay in place, to assure that contaminants do not get between lubricating surfaces, when operating temperatures are too high to use oil, and when frequent oil lubrication is not easy to do. A grease whose consistency is properly chosen for its operating conditions is easier than oil to keep between lubricated surfaces. Now, as long as grease remains semi-solid, it tends to stay where it is placed. Now, liquid oil is much more likely to flow away from where it is needed. Under conditions when both oil and grease